Now that we've gotten to know trees a little bit, we're going to talk about something called minimum spanning trees. So to sort of give us an idea of why we care about minimum spanning trees, we're going to consider the problem of creating a network in a cost-efficient way. That's going to help us define what weighted graphs are, and then from that we're going to define what spanning trees are. And finally, we're going to define what minimum spanning trees are, which is the ones that we're kind of interested in our network creating problem. And finally, we're going to look at some examples. So imagine that you're creating a network of sites. You have some different sites that you want to connect, and we can make direct connections between the certain sites, but that has a certain cost associated with it. So we don't necessarily want to do that between all pairs of sites. But we are happy as long as the sites are at least indirectly connected. In other words, you can get between any two sites by routing them through other sites if necessary. And finally, each direct connection has a certain cost for constructing connection. And we want to look for a model for this situation. And if you look carefully, it looks like we want to use graphs. So how does the graph model work for this network problem? Where the sites that we're trying to connect, those are going to be our vertices. And the fact that we're connecting them said that the edges are the possible direct connections between the sites. And so if A and B are sites that can be directly connected, then A, B is an edge. Now we have another thing that's going on with this that's kind of new, right? Because each connection that we make has a certain cost that's associated with it. So each edge has a cost associated with it. And that leads us to define the term weighted graph. And a weighted graph is a graph where each edge is labeled with some kind of real number. So if G is a weighted graph, we can think of that labeling as a function that if you give me an edge, I can tell you what the weight is that goes along with it. So if W is the function, it has inputs, the edges, outputs are real numbers, and the output for each edge is the weight or cost that's associated with it. So in our model, the weighted graph tells us what possible networks we can build and how much each of those connections is going to cost. So now that we have that situation set up, we might start asking, well, how is this going to help us solve our problem? How is this going to influence which of our connections we're going to build? Because again, we probably don't want to build all of them because that's going to be too expensive, more expensive than we need. So we got to think about what our values are when we're looking at this. And there are maybe lots of different things that you value, but here are 3 of them that you might value, right? That you might. You're not required to. Everybody's entitled to their opinions. So we definitely want all the vertices to be connected to one another. After all, we're creating a network. Right? And these could be directly connected or indirectly connected is okay too. We also don't want to spend too much money, right? So we might want to minimize the cost. But on the other hand, we might want to have a little bit of redundancy in the connections in case one of the connections break down. We don't want to have a connection break down and completely disconnect our network. So, I mean, those are 3 things that you might be concerned about. We're going to ignore the third one. Not that it's not important, but for our particular circumstances, it's not going to really influence us. We're going to prioritize the first 2 bullet points. We want the vertices to be connected, and we don't want to spend a lot of money. And that's going to give us what we call a minimum spanning tree. All right, so let's let G be a weighted graph. A spanning tree of G is a subgraph of G that is a tree but also includes all the vertices of G. Note that it may or may not include all the edges, but it does include all the vertices. A minimum spanning tree of G is a spanning tree that has minimum weight among all the spanning trees. So that's the one we're looking for that will connect every vertex. It's going to be a tree, so it's connected, but then also has the minimum cost. So why a tree? Well, that's a good question. First of all, as I mentioned before, trees are connected, so they'll connect all our sites. And it also turns out that by some of the work that we did before, trees have the fewest number of edges of any connective graph with the same number of vertices. So in other words, if I have a connected graph with 10 vertices, the fewest edges I can get is 9, and I can only get that through a tree. I get that through any tree as it turns out, but I do need it to be a tree. Now the downside of this is if you break one of the connection, that's going to disconnect the graph, which means that some sites are going to be disconnected from other sites. But again, with the problem that we're working on, we're not worrying about that, but in real life, you would worry about that. So let's look at an example of a weighted graph. So here is a graph with 6 vertices, and notice that each of the edges has a number next to it, and that's going to be the weight of that particular edge. So for instance, the weight of the edge between A and D is 3, or if you're thinking about those sites that we're trying to connect, the cost would be 3. So here's an example of a spanning tree, and the what we're looking at for the spanning tree, in case you can't tell, the blue edges, those form the spanning tree. So if you ignore the black edges and just look at the blue edges, you'll see you actually have a path, E to F to A to D to C to B. And that's, of course, a tree because there are no cycles, but it also includes each of the vertices on the graph. And now if we look at the cost for making those, the weight is going to be 31. Unclear at this point whether that's going to be a minimum spanning tree or not. Turns out it's not. So if we want a minimum spanning tree, here's one example of a minimum spanning tree. Again, we're looking at all the blue vertices. Or not the blue vertices, the blue edges, those form the spanning tree. You notice that they include all the vertices of the graph. And at this time, if we add up all the weights, and I'll let you do that if you want to pause it, it turns out you get 17, which is a lot better than we did before. So even though it had the same number of edges, both of them have, both of them have 5 edges. It turns out this one has a lower total weight, a lower total cost associated with it. All right, so now that you've gotten some experience thinking about minimum spanning trees, it's time for you to work on the in-class activities. The PDF file included with this video is called Minimum Spanning Trees.